Hi all, in Unit 8 we are learning the reactions that go through an enolate. An enolate is an anion that is formed by removal of an alpha hydrogen of a carbonyl compound. Thus, we are interested in how easy it is to remove this alpha proton of compounds such as aldehydes, ketones, and esters. And by understanding the acidity of these compounds, we have a better understanding of the reaction, but also what kind of base we can use to do these enolate reactions. The pKa's that I want my class to memorize are shown here. They are of the aldehydes, ketones, and esters, and also of the dicarbonyls. Again, just to reiterate, we are interested in these acidities because we want to form the enolate. And quite simply, an enolate is formed by reaction with a base. Let me show you how the enolate is formed. Here I have an aldehyde, but this could be a ketone or an ester. There has to be a hydrogen at the alpha position, so the alpha position is the one next to the C double bond oxygen. Here I use hydroxide to remove that alpha proton. And I want us to write first the enolate anion that has the negative charge on the oxygen. Now this has resonance, and the resonance can proceed this way to put the anion on the carbon. Depending on the source, the textbook, or a Google search, you may see the enolate written in either of these forms, but the more contributing resonance structure is the enolate where the negative charge is on the oxygen. Another thing that you may want to note is that we do create water, and that's important because look at the equilibrium. The equilibrium is favoring the unreacted aldehyde. So we get a little bit of the enolate, but the majority of the carbonyl compound stays as the keto form or the neutral form. That will play a big importance when we talk about reactions, but in this particular video, I want to focus on the pKa's of these carbonyl compounds. Later on, we'll talk more about the choice of base, and also why, when we do the mechanisms, or show the mechanisms of these reactions, why we want to proceed via the oxygen anion. But for now, let's talk about the pKa's. There are 3 questions that I want to address in this video. The 3 questions are: why is an aldehyde alpha proton more acidic than the ketones? Why is a ketone's alpha hydrogen or alpha proton more acidic than an ester's? And why are the alpha protons of a diester more acidic than a monoester? And again, these are our structures we are going to be using. Let's tackle the first problem, or the first question. Why is an aldehyde alpha proton more acidic than a ketone's? I'm checking these two out over here. When comparing the reactivity of an aldehyde and ketone, we want to remember 2 things. The first thing is, the more stable the conjugate base, the more acidic the acid it came from is. That applies to almost every acid-base problem that we have. You look at the stability of the conjugate base to determine how acidic the acid is which gave you the conjugate base. Now specifically to the aldehyde and ketone discussion, the second point is important. Alkyl groups are electron donating. They push electrons away via hyperconjugation. So if we take a look at our ketone, you could draw the dipole, or the, we could call it the dipole arrow, as this, pushing electrons into that carbonyl. We don't have an alkyl group here. Again, this alkyl group is electron donating group. Now, why does that affect the acidity? Let me show you how this electron donating group affects acidity. If we draw the conjugate base of both the aldehyde and the ketone, we get the following. Here I have drawn the acid-base reaction between the carbonyl compound and hydroxide. We gotta realize that, again, we are deprotonating at the alpha carbon, and we get these two conjugate bases. If we could figure out which one's more stable, we could figure out which one is more acidic, or why the aldehyde is more acidic than the ketone. Because we're making an anion, take a look at this situation for the ketone. We are pushing electron density into or closer to the anion charge, so we're not spreading it out. So this is a little bit destabilizing. This electron donating group destabilizes the anion. We still have pretty good resonance, okay, but it's a little bit less stable than this anion up here. Our conclusion is that this conjugate base is less stable. This conjugate base is more stable, and hence we have this one as more acidic. The aldehyde is more acidic than the ketone. Okay. Now, I just want you to recall your pKa's from Organic Chemistry 1. Let me find that real quick. Here, the aldehyde, alpha hydrogen, the ketone alpha hydrogen, they're around 17 to 20 pKa units. But if we look at any other hydrogen connected to a carbon, for instance the alkanes, or the alkenes, or the alkynes, all of those are less acidic, right? Less acidic than our carbonyl compounds. Even for this hydrogen right here, we could have resonance. Let me show you that. And we can have resonance. But even with that resonance, it is still less acidic. See, it has a pK 43, less acidic than our carbonyl compounds. Let me just finish the resonance here. Negative charge there, double bond there. Okay. Well, that's because we know that negative charges are more stable on oxygens than carbons. We have no oxygen here. The anion is always on the carbon. So that's another thing that we could make note of. The carbonyl compounds have a greater acidity because of this oxygen right here. Hopefully, we were able to answer the question for you all. Number 1, why is an aldehyde alpha proton more acidic than a ketones? It's because, again, the alkyl group is electron donating, which destabilizes the anion charge. The second question is, why is a ketone's alpha hydrogen more acidic than an ester's? Let me draw, or you could pause the video. Why don't you draw the acid-base reactions now, comparing the ketone? We have it right here already. Let me compare it to the ester. Okay, when we look at the pKa's of a ketone versus an ester, you see that the ester is less acidic. Can we explain that by analyzing the conjugate base? So here's the conjugate base, the enolate form of the ester. And again, we do have this resonance, so that's good. The same resonance that we would have up here for the ketone enolate. But something's interesting with the ester. In the ester, we have a competing resonance. Now, it may not seem very important because the contributor is definitely the minor contributor, but it is still, it still exists. This is a competing resonance. And obviously that comes from moving the lone pair to make this double bond and kicking this pi bond to the carbon to make it a negative. The thing about this competing resonance, even if it's a very minor contributor, is that it does not stabilize the charge. It does not stabilize the negative charge. So this competing resonance does not stabilize the anion. See, that negative charge is still stuck on this oxygen. It didn't delocalize. Did not spread out or delocalize. In fact, it made more charge, but we're not concerned about that. So the issue is, this anion right here, is it stabilized or is it destabilized? Relative to, we're comparing it to this one, the ketone. So the ketone enolate, we do have this slight destabilization, okay, but here we have a bigger destabilization because now by resonance we could see that by this competing resonance we are not spreading out this charge. I know that I am focusing on, again, how are these conjugate bases destabilized, but still the fact is these conjugate bases are actually more stabilized than any of the conjugate bases you could get from these molecules. See how the pKa's are still higher than any of the pKa's that we have here. Maybe ester, okay, is a little bit close to the alkyne, but all the other ones, they're definitely much, much higher than any pKa's that we see for our carbonyl compounds. To sum up, again, why is the ketone a little more acidic than the ester? Okay, question number 2. That's because an ester, its conjugate base has a competing resonance that does nothing to help stabilize the anion that we initially make, the anion of the enolate. We have one more question to answer, which is, why is the diester more acidic than the monoester? And if we take a look here, by the way, what we've talked about so far is the differences between these three in the top row. And what do you notice about the dicarbonyls? In general, see, the diketone is much more acidic than the monoketone, or the diester is much more acidic than the monoester. And now if we have a combination, a ketone ester, that's going to be the intermediate in between these two. Hopefully that makes sense, that we have these relative acidity strengths the way they are. Let us talk about these two, and this is pretty easy. I think all of you can see this already. We have multiple resonances that can stabilize the anion if we make the anion on this middle carbon. Right, this would be the most acidic hydrogen. Same thing here. Okay, and same thing here. Even for the diketone, this is the most acidic proton. More acidic than this one. This would be, I would say, 20, just like here. But this is 9. Let me show you those resonances. Maybe you can draw, what can you draw? Draw me the conjugate base of the diester, and then draw the resonance structures that can stabilize an anion. Alright, maybe you've seen a couple of interesting things when you drew out the conjugate base and the resonance of a diester. Here we are comparing the diester with the monoester. The first thing that I didn't realize until I drew this water molecule is that, the equilibrium arrow now supports the formation of the product because the lower or the weaker acid is water. And 15.5 is weaker than 13. You know that equilibrium favors the weaker acid. We didn't get that in our other cases because in each case, these 3 pKa's are greater than 15.5, so that's why the equilibrium arrows are facing to the left, to the reactants. Okay. So that's one thing. We switched equilibrium. But don't forget, our main task is to explain why the diester is more acidic than the ester. That's because of resonance, obviously. And here I have our conjugate base. To get our second resonance structure, I'm going to put the negative charge on the oxygen on the left. And to get our third resonance structure, do you know how to draw the mechanism arrows? you push this pi bond to the adjacent bond, and you kick up the pi bond to this oxygen to get our third resonance structure. Okay, so that's why the diester, you have more resonances, more favorable resonances than you do for the monoester. Okay, so I'm not drawing this competing resonance for this conjugate base. It does exist, but again, we're comparing these two resonance structures versus this conjugate base, which has 3. Hopefully that answers the 3 questions that we were tasked to answer. Now, the last thing I want to say is that, we looked at the diester, has a pK of 13. Do you understand why the ketone ester and the diketone have lower pKs? These two are more acidic. Again, it's the idea that this alkoxy group has a competing resonance. So when we don't have those alkoxy groups, your diketone now is more acidic than the diester. Hopefully you can see the trends between these 6 carbonyl compounds, which we will be using to make enolates to do several reactions